Okay, don't be scared by the little circle, but we're going to talk about standard entropy and the delta S with the little circle for a reaction. Great news. This is exactly like the standard delta H reaction. Things have to be in their standard state. The values appear in the appendix. The delta S standard of reaction is the sum of the number of moles of products times the entropy of the products minus the sum of the number of moles of reactants times the entropy of the reactants. So this will function exactly like it did when we did delta H. You'll get your values from the appendix, do products minus reactants, multiplying by the coefficients as you go. Again, and as always, watch your units, and the standard entropy for an element is not zero. So this one piece is the only major departure because we only have zero entropy at 0 Kelvin. Just look for the entropy for everything when you go to the table, because even if it's a pure element, it will have some inherent entropy associated with it. Like O2 as an element, delta H standard or delta H formation would be zero because that's the element in its natural form, but that's a gas. It's moving around, right? That is the standard state because we're operating at 25 degrees. There's a lot of disorder associated with that. Now, if everything is in its standard state, then we can have a standard delta G that's calculated from the standard delta H and the standard delta S. And given a reaction, you now know how to, one, use the enthalpies of formation to find the standard delta H for a reaction, how to use the entropies to find the standard delta S for a reaction. And if you're at 298K, which is the standard temperature for standard conditions, you could calculate the standard delta G reaction. Or you'll notice that there are delta G values in the appendix. It's the delta G formation. So the delta G formation has already incorporated the enthalpy of formation and the standard entropy. So the standard delta G reaction you can find using the sum of the number of moles of products times the delta G of formation of the products minus the sum of the number of moles of reactants times the delta G of formation of the reactants. So you have multiple ways at getting at delta G and the components that are associated with delta G. Now, when you are doing a problem, look ahead to the other parts of the question just so that you don't have to solve everything twice. Delta G formation is a perfect shortcut in many cases, but especially if I'm trying to put everything into one test question, the chance that just doing delta G formation will be what you need to do, it's probably pretty low because I'm going to want to also test you on delta H and delta S. So just skip ahead and see what you're going to need because you might be able to save yourself some work that way. So manipulating reactions and delta G, we can do this, and more great news, it's the exact same rules as the delta H manipulations. So if I take a reaction and multiply it by a factor, I can find the delta G for the new reaction by multiplying it by the same factor. If I reverse the reaction, I change the signs, which we kind of got at with our initial example about favorable, not favorable, or spontaneous versus non-spontaneous, right? You drop a book in a gravitational field, it's spontaneous or favorable. When you completely reverse what you did and pick the book up, that's not favorable, non-spontaneous, right? The amount of delta G associated with that would have the same magnitude, they just have opposite signs. When you add reactions, you will also add the delta G values.